All right, guys, I'm going to try to go over a couple problems with you. I'm going to try to share my screen. Hopefully, that works as well. Let's see if this works here. This is problem number three. Problem number three. Let's look at it real quick. For flights of a particular airport, there's a 30% chance of flight being delayed because of icy weather. Whenever that shows up, that lets me know I'm about to do a tree diagram like we talked about in class today. Okay, so 30% is being delayed. That means 70% is not being delayed. So we're going to draw our branches like that. If a flight is delayed, which means I'm going on the 30% side, there's a 10%. It's also going to be delayed because of a mechanical problem. So we got another branch, 30%, another branch, 10%, and another not branch of 90%. Okay. If the flight is not delayed, so now I'm on the 70% side. All right. And I'll show you a diagram of that in just a second. There's a 5% chance it will be delayed because of a mechanical problem, which means 95% it won't be delayed because of a mechanical problem. So that tree diagram looks like this. Hopefully you can see this. Hopefully you can see this. All right, so 30%, there's a 30% chance for weather delay. After that, there's a 10% because of mechanical. That means 90% it won't get delayed because of mechanical. All right. 70% it won't get delayed because of weather. From there, 5% chance, if it's not delayed, it'll be because of mechanical. That means 95% chance of it not getting delayed from the weather, will not get delayed from mechanical. Usually about 66.5% of these airlines, if we picked one at random, is going to have a chance to not be delayed. All right. So, what's our question? What is the probability that the flight select will have at least one? So, I need one cause of delays. There's two types of delays. I need at least one. What's the probability of selecting with at least? Well, let's just count. Remember what I said about we'll have at least one? Remember that? Let's see if I can pull it up. Right here, when there's a probability of at least one, that's really one minus the probability none will be delayed. All right, so let's look at that. Let's look at that. Well, this is one, right? And at least one. So this is two, but that's still at least one. So we're going to count this 0.03. Here is at least one, right? So I'm going to count this 0.27. It's not delayed here, but it is delayed here. That's at least one. So we're also going to count the 0.035. And this not delayed, not delayed, right? That's the probability of one minus none of them. So we can do it two ways. We can add all these up. We can add all these up. Or I can say one minus the probability of them not being delayed at all, which is this one right here. All right. Or I could say 0.03 plus 0.27. You guys that were with me in class, you remember we add up and down and we multiply across. 0.35, that's also 0.335. That should be your answer right there, okay? All right, let's go quickly through these. Electrical system, what's the probability? If they're independent now, that means one really does not have an effect upon the other. And it also means I can multiply when I'm talking mathematically. So really, we're going to go back up to here. The system will function good or successfully if at least one operates. So, well, remember, anytime we're dealt with the probability of at least one, that's the same thing as saying 1 minus the probability none of them work. Well, if the probability of them working is 3/4, let's do this. I want to say 1 minus the probability of it not working, 1 minus 3/4. Well, wouldn't that be 1/4? Right? And we've got 3 of them, so I can multiply them. So let's just multiply it out times 1. Hopefully my calculator will do this for me. Times another 1/4. What did I do? Well, I've got 3 of them that if they don't work, that's the probability of them not working, right? So there's that probability of all 3 of them not working. Well, I want to know what's the probability that they will function successfully. Well, that's 1 minus this answer here, which is this, but notice they want us to give it to us in a fraction, and we could have written this out if I was in class, but here's an easy trick for you. Go to math and convert it to a fraction. What we got here? There we go. That's the same thing. That's the same thing. Okay. Hopefully that helped you. I got to move on. Got to move on. Independently. Let's see. Oh yeah, they are independent. So really, the problem we can talk about this one a lot, but we can do a two-way table on this. I think I set it up actually. Yeah, I did. Let me move my face out of the way. You can read the problem, but it says out of 80 people surveyed for guys, 60 of them were brown. We don't know how many were not brown. And we don't know how many female were brown, but we do know the total females because if 80 were males and I had 200 total participants, that has to tell me that 120 females were a part of the survey. Well, if something is independent, that basically means in a two-way table that the probability or if something is independent, that means that their probabilities will actually equal out kind of to each other. So the probability of 60 over 80 has to be the same as the probability of a female being brown to 120. All right. So that would actually look something like that. I mean, we can do it a couple different ways. We can say, what is the ratio of 60 to 80? Right. That's 75 or 75%. Well, if they're independent, that female ratio needs to be pretty much the same as well. So what is 75% of 120? If they're independent, well, that's what it is, 90, if that's an answer choice. There are 90, how many female students surveyed? Yeah. Are expected to have brown eyes? Yeah, there should be 90. Should be 90. That's your laws basically of independency. And we could have done this, if we wanted to. The probability of, B given A has got to be the same as the probability of B itself. And we could have worked that out. Probability of A and B, we can multiply there. Different things that we could actually talk about. All right, let's move on. Move on. Number 6, we've done before. All right. And again, if you need the reference sheet, it's right there. Probabilities and distribution. It's this part right here. This one right here. Probability of A given B. That's the same thing as probability of A and B divided by the probability of B. That's how you can tell if they're independent or not. Do those things equal out? Well, there's the probability of A and B, right? And if I divided that by the probability of B, what's the problem? Let's just do this one. Heck with it. What is that? 0.375. If I divided that by the probability of event B being 0.5, if they're independent, I should get this 0.75. And there it is. So these things are independent of each other. There's another test that you could actually do to make sure, right? So first of all, I'm gonna cross out these choices that are not independent, right? Not independent means that yeah, one event, kind of changes the outcome or probability of another event. That's what not independent means. Let's see. Oh, yes, not mutually exclusive, and independent. Are they able to happen at the same time? Well, they've already given us the scenario that it can happen at the same time. So that's what mutually exclusive means. They're not mutually exclusive. So they can happen at the same time. All right. All right, let's keep going. We've had that one before, I believe. Oh, here is another one that you need to draw out a tree diagram for, please. Probability of purchase mineral rights to the first mountain is 0.55. So draw your tree diagram. The probability that it will purchase to the second mountain, 0.4. So I think I drew this one. Yeah, here it is, right here. Probability that it will purchase the first one is right there. And probability that it'll purchase the second one is right there. And not purchase the second one is here. Okay. Not purchase the first is 0.45. Purchase the second is 0.4. Not purchase the second is 0.6. And I gave you all of those, the probability of A and B actually happening. All of those probabilities multiplied together. There it is. Here's the question. What is the, get away. Oh, I'm waiting on this to go. There you go. What's the probability that it will purchase mineral rights to exactly one out of the two mountains? Well, where did that happen at? Well, here is exactly two right here, these two, right? I'll put it in red. That's one, that's two. Here is exactly one, right? This one, I did not purchase the first, but I did purchase the second. So it looks like these two right here, which is these two scenarios happening here. The probability of selecting both of these, add those up. I think we get an answer. I know what it is in my head. I want to make sure I do see it. I do see it. Okay. See if you can figure that one out. Again, if you don't understand it, let me know. You guys that wasn't here Monday, we did probability trees to help us with probabilities. All right. This is another one. You would actually, this one, I think, it's written kind of backwards. Start it right here. If 5% of the certain population has the disease, right? Start your tree diagram from there. If 5% has it, well, doesn't that mean 95% does not have it? Then it says 90% of the people who have it will have a positive result, right? So you're going to go from the branch of 5%, you're going to go 90%, then you're going to go 10%. 90% will have a negative result, okay? If 5%, what percent of the population would test positive for the disease? So you're looking for all of the ways they would test positive, okay? I don't think I wrote that one down, but anyway, do a tree diagram, see what you get. This one here. Oh, okay. Let me see. You got the probability of A, 36.5. Household has dogs, cats. So I've got an A and B scenario. If one of the states, one household was selected at random, what's the probability that the household owns a dog or a cat? Um, well, it looks like to me, it doesn't tell me if anything's shared. I don't think I've got enough information here. Let's see. I don't have that rule written down. Let's see. Yes, we do. It's right here. All right. So the probability of A or B, which is what we're trying to find out, dogs plus cats minus what they share. Here's the problem with this. It doesn't tell us what they share. We can't necessarily assume that they share anything. Um, I don't think we're given enough information on this one. Is that a not answer choice? Yeah, I think it's this one. I think we don't have enough information on that one. Okay. All right. That's all I'm going to spend time with you on. Okay. Uh, and if you guys have any questions, you got to let me know. We are going to have a test on Thursday. Wednesday, we're going to study, hopefully, do really well on that. And we'll see how we do. Okay. All right. Have fun, everybody. And text me or chat with me on Canvas if you need to, or anywhere. Just write me an email and I'll help you out. All right. See you later. Have fun. Be good to my son.